Hello YouTube viewers, welcome to my channel STT. In today's show, Future Friday, we're going to talk about quantum computers. So let's dive right into it. Well, before we understand quantum computer, we have to understand computer. So what the heck is computer? Well, if you simplify all the magic about it, it's just a logic device. Now, how the heck logic device is made? Well, it's made using 2-bit logic. What the heck that means? That simply means because we are using electricity as the medium, electricity only has two states, either is on or either is off. For our computer, we chose that. So we took that like either on or off, which we call bits, bit, 0 or 1. Then we send that data into what we call logic gates. Now these logic gates have many configuration, whether they are like if A and B is on, then they're gonna give you out like A plus B, and if it's like A and B is there, then it will do A minus B. Logic gates, these are something that you must have studied in class 11 and 12 in your school. So these are the logic gates. Now once you combine all of these logic gates, then you get a processor. That's the reality of all the computer processor, be it in your television, be it in your mobile phone, be it in your smartwatch. That's all there is to it. So it's just logic gates working together in a circuit that is giving you the whole processing reality. Now how the heck you interact with it is basically done through programming, basically machine language if you want to consider it. We talk to these things like we tell them arrange yourself in this way or this way, or if you receive like receive this signal, do that. So that's all there is to it. Computer, basically logic gates. So what's the issue with this? Because computers are fine, computers are dandy, they are working, they are in your iPhone, they are in your satellites, they work. So there is no problem with them, they do not work. But then what's the limitation? Why the heck we want to go into quantum computers? Well, logic gates are physically made of transistor. Now transistor is all there is to it is just a switch. Basically it says electricity is either on or electricity is either off. Now the tricky part is it does not have moving parts. So you do not think it's the same switch as like in your light board. Basically you do not go there is no moving part into that. So it's a what you call semiconductor, where it can become conductive or non-conductive depending on a signal. So we make everything out of transistor. Now transistor, in the early days we started to make them small, then we started to make them really small. This is the era of Apollo program, and this is the birth of what we call integrated circuit, basically making them so small that you need a microscope to see them. And then we started to make them really small, aka starting to measure them in nanometers. Now to give you a context of that, your hair is thousands of nanometer. So it's a very small scale system. To give you a context, that like early processors like Pentiums and all that, they were around 70 nanometers to 50 nanometers. Then we started to shrink that down to 30 nanometer, then even shrunk that down to 22 nanometer. Now here's something interesting happens once you start to shrink them down in single digit, aka 7 nanometers. Once you make them small enough, the semiconductor's ability to stop electricity goes to zero. Basically your transistor, all it's doing is whether it's letting the electricity flow or not letting it flow. Now letting electricity flow is the easy part, stopping them is the hard part, because once you make them your system small enough, basically like let's say a few atoms across, electron can simply say it can just teleport through. Quantum teleportation, it's literally that's what is classified as, like it will just tunnel through it, like you quantum tunneling is like oh I don't care. So that's the problem, it will make your transistor ineffective. And we already started to have consequences, because many of the modern designs, they have like clever geometries to reduce the probability of that happening, and even then they have many circuits built into them to do what we call error correction, because it always happens once or while, it will always happen, it's just rarely the probability. Let's say it happens once in 10,000 operations, not an issue, and it only happens once, you can correct it. Then it happens like 100 times in 10,000 operations, now you are talking about a bad processor. What happens if it happens like every 100 times? Yeah, your processor is useless. That's the problem, we cannot make them any smaller, because right now stopping electrons is nigh impossible at this scale. 7 nanometer, 5 nanometer, 3 nanometer, and at 3 nanometer, 4 nanometer, like we do not even have a geometrical answer that is like it may allow us to reduce the probability of electron tunneling so much. So we have to stop, like we cannot go any smaller, we cannot make our processor any more power efficient in the core level. The logic gate has reached its maximum potential. So at this point in time, will we have like what I am already saying, we have already, yes, there is still a lot of room of improvement. We're gonna have better design, we're gonna have cheaper design, we're gonna have more efficient use, all of that just will happen. So we have like at least 5-10 years of momentum left, so we don't have to worry about it. But the engineers who are developing the next generation chip, they are actually worrying about it. It's like, dude, okay, I got this, I made this 7 nanometer, 5 nanometer is 10 times more difficult, manufacturing is 100 times more difficult. Then we have to make what after 5, because you have to know these people, that's their job, like make better and better processor. And you must have heard of Moore's law, which is like, FT 18 months it gets doubled. So that's the reality. We are reaching the maximum saturation point. So we cannot do much. But on top of that, even though we reached a point where we cannot make a single processor very complex, we learned something interesting. It was like, how about putting hundreds of them in one place, which we call supercomputer. Now supercomputer allowed us to become godlike in our reality. Right now our weather prediction is so damn accurate that if your reliable news source says that it's gonna rain, it rains. Like in India, like in my own family, it's becoming a joke. Like if a newspaper says it rains, it rains. If it says it does not rain, it does not matter how many clouds are in the sky, it will not rain. Like our weather prediction went from, oh, this whole coast will be hit by hurricane, to like, okay, this districts will be hit by it. We are becoming that precise with weather because supercomputers are that awesome. However, they have a limitation, because our physical reality, the world that you see and interact in, have two components to it. The component number one, the thing you see, which we call Newtonian physics driven thing. Basically you can touch things. So this is Newtonian physics. This is what you know. This is how you understand. Like you're throwing a ball, you understand what happens. But if you go down to atoms, you're still more or less in Newtonian physics, because you have to understand that atom is the building block of matter. Now what happens is, if you go below that, you lose the property and identity of the material. So basically one electron from a copper is the same electron as a gold. So that's the reality of it. You cannot go below atom and still retain the properties of an basically atom. So once you go there, what happens then? Because it's there, like electrons are there, protons are there, they are reacting in a different world, the world which we classify as quantum world. Now quantum world is YOLO, like it has so many weird properties where it teleportation is one of the normal behaviors it does. To give you another aspect, it has what we call superposition. What does that mean? That simply means it could be, let's say, position number one, position number two, it could be anywhere between these positions, anywhere. Not like, okay, 10 to 90, 20 to 80. It's not like that. It's like infinite number. It's like, it depends on your measurement equipment. It can have that many steps. So why does that matter? Do we need to understand something that deep, something that profound? Short answer, absolutely. Because when these quote-unquote superposition collapse, they affect the atom. When they affect the atom, they make the atoms behave in certain way. What happens with that? Well, your DNA is made out of atoms. Your protein folding algorithm is made out of these things. So to understand these things, to understand how to make vaccines, to understand how the heck you're gonna make sure that this drug directly goes to where it's supposed to go and does not go anywhere else, you have to figure out how the heck it's gonna interact with protein. And to understand in that level, molecular level, you have to understand quantum physics. That is why. And if you want to simulate those things in a normal silicon computer is like, peace out, I cannot do this. Flat out, it cannot do that, because the probability goes to infinity. So that's the issue with it. Not only is we are reaching at maximum point, we no longer can push our understanding of reality using these puppies. So a new way of thinking started to come in the forefront, and as in this started as early as 1970. Richard Feynman and all that jazz started to pour a lot of serious research into this, like, can this be done? So physics has been laid down quite early on. However, making an actual, like, you have to understand that, like, Einstein is the guy who came up with the idea of laser, then some other engineers came up with the actual laser, then some another engineer came up with barcode and CD and DVD. So there is a giant gap. So the thinking about 1970, people are thinking about that, yeah, that's happened. That's normal with everything. So quantum computers, now idea is the same way an electron is an electron, a superposition behavior is the same as every other damn thing. So if you can simulate quantum worlds, you can extrapolate data out of it, and you're like, okay, this is how it's gonna behave. So that's the whole point. So if we have quantum problems, basically we have to understand how the microscopic behaves. Microscopic is like, nanoscopic would be the correct word. How the heck nanoscopic worlds behave, we have to figure out how the heck quantum realms handle it. Why? Because quantum worlds dominate at those reasons. At small scale, quantum physics is like, I'm your guide. At big scale, Newton is your guide. So we have to go to quantum physics, otherwise we are limited on what we can do. So same way I specified, a transistor is a building block of a normal computer. A superposition is the building block of a quantum computer. Now superposition has two states. Either it's off. Now what the heck off means here? Off simply means you read and directly observed it. That's why you will always hear people say, like, observation changes the outcome of an experiment. That's what happens, because the moment you observe it, or you heat it up, or you probed it with a voltage probe or anything, the moment you put it in, like, hey, tell me, it's like it collapses. It goes from infinite probabilities to a fixed its probability. That's the off state. Then you have on state. Now, interesting part happens when it's in off state. It's in superposition. What does that mean? Infinite probabilities. Literally. In the early days, our computers were not that good. So that time you will hear people saying like, quantum bit is 8-bit because like, it has 8 different states. That depends on your mathematics and your algorithms and all that jazz. But physics wise, it's infinite. So normal computer is like on or off. This puppy is like off, or when it goes on, it's like infinite states. Depending on your design, depending on your complexity, you can have like 5 states, 12 states, 36 states, as much as you want, or you can directly process in that itself. That is what we want to explore, because this superposition is quote unquote infinite. We have to exploit these properties. So the reason for trying to exploit this puppy is like, you have seen hundreds of these kind of graph. Basically a classic computer is like one by one by one, it's trying to solve something. Quantum computer solves everything at the same time. Why? Because it is in quantum state. It is literally in superposition. It's like, if you are designing your things correctly, it will be like, okay, what happens 2 plus 2 equals 5? What happens if 2 plus 2 equals 3? It will go through those and it will come up with like, yeah, those two are wrong answer. Then it's gonna print out 2 plus 2 is 4. Now it may sound counterintuitive to do it this way, but for a complicated problem, that is the only way to do it. So that is why we want to exploit this superposition. That is the main thing that we want to do. So how the heck we achieve this superposition? Now you have to understand this. Everything, every atom, every molecule has this superposition and superposition collapsing. That's what's giving matter our reality. Like, that's how your reality works. However, you have to understand this collapsing happens through hundreds of things. Basically probing, measuring, observing, everything. And heat also. Now that is the critical aspect. Normal molecules, even a big molecules, can achieve this quantum state where they are like yellowing around. But problem is, to make sure they are yellowing around, you need to cool them down. And I mean really cool them down. So we are talking about the temperature. Basically, we have to cool it down. We have to cool it down so much that outer temperature looks like a hot oven. We have to cool it down to 0 Kelvin, aka absolute zero, or try to get as close as possible. Basically, these are temperatures so low that normal superconductor starts superconducting way before that. It's like, and whenever you see some diagram or images like this, all this is just a cooler to allow something in small, something like a computer processor here, to go down to those temperature. That's the reality of it. It's like, oh, here we have liquid nitrogen temperature, here we have liquid hydrogen temperature, here we have liquid helium temperature, and here we have liquid helium-3 temperature. So yes, helium-3 is also used here. So it's that cold. Once you remove thermal management from that point, you do not allow atoms to collapse. Basically, atoms have to stay in what we call in superposition. And then again, you have to isolate them from electrical noise, vibrations, radiation, everything. Like these actual chips, they are put in a place where it's like nothing interferes with it, because the moment even a stray X-ray photon goes through it, it will collapse the wave function. So that's how we achieve superconductor. So basically quantum computers, we have to go to superconducting temperatures, superconducting isolation. It's like absolute vacuum. Everything is like very the only way to describe is like void. It's absolute void. There is no radiation, there is no temperature, there is no vibration. And this processor, it has no energy consumption. Literally at that temperature, again, it's a superconducting state, so it has no heat output of it. It's not like you are processing from it. It's not gonna do anything with that basically energy. It's not heating up like your processor. And how much it can do, that depends on how good your algorithms is and how much superpositioning you are using. So what are the use of this contraption basically? And if you when I said that that processor has no energy consumption, that's absolutely true. However, you have to understand that the cooling puppy for that puppy is around 20 kilowatts of energy consumption just for cooling. And yes, it will not exponentially will become more expensive if you want to cool it down, but it will become like MRI machines. How MRI machines require liquid helium top-ups to keep them operating, same you have to do with quantum computers. So do not think quantum computer will ever become something that you can have in your home or even in small hobbies. It's something so big, like only few servers will afford to do that. So why the heck you want to do something that complicated, like that, that hurts your brain, superposition, infinite probabilities and all that jazz? What's the point of that? Now point is because our world inherently runs on quantum basically principles and reality, it inherently has infinite probabilities. Basically, if you want to simulate something precise enough, basically we know DNA, we can simulate it roughly enough. Now the moment you want to simulate it accurately, it's like, I'm gonna say this drug I react this and it's gonna knock out this phosphorus atom. Good luck with that. Good luck. Normal classical computers like, peace, I'm out. So to understand how the heck that happens, you have to understand how the heck quantum computer happens. Now, either you can simulate every single interaction which requires infinite number of that, or you can just run it through a quantum system. So that's why we want to understand this, because to understand molecular behaviors on a fundamental level, like our DNA, this is the reason we cannot make basically a vaccine as of now of basically HIV. Why? It's like HIV literally infects the DNA that protects us. Like it goes through the immune system, and it's like goes into the headquarter and corrupts that point. How the heck that is doing that? Like, because you have seen how easily we have created vaccines for other things, like from polio, like I'm saying quote unquote easily, it's like from polio to pox and all that jazz. It's like we understood this like because our basically defense headquarter was intact. HIV goes through that defense headquarter. How the heck it's doing that? And how the heck we make a vaccine that does not destroy the headquarter? Like, it's because, oh, there is an invasion in the headquarter, let's blow that up. Or how the heck we make sure the chemotherapy only goes to the place where the cancer is there. All those things happens on a macro scale. Those macro scale are affected by quantum principles more than the classical physics and Newtonian physics. So we have to understand this. So simulation will become a huge game changer on this. So any corporation, let's say a drug company, figures this out, like they have actual high end like capable quantum computer which can actually do things, not just some lab experiment, like actual computer, they're gonna be printing money in less than few years. They will be like, I don't even count how much money I have. Like that's the reality of it. Like it's gonna print money. Then we come to advanced encryption system. Now, one thing you have to understand about encryptions, all the encryption is going to do is delay the hacker. That's all it's going to do. There is no unbreakable encryption if physics does not allow that, because you have to have the ability to break it, otherwise you cannot use it. So you may like key and all that, that means there is a small probability that you are using in order to unlock it. So physics does not allow you to have that. However, our current approach with basically encryption is very simple. Is make that probability so damn small that yeah, you can hack this RS encryption, but it will take you 1000 years or 500 years to on a supercomputer. Then it's like, a hacker cannot brute forces. See, but to understand this, because superposition of an atom acts in a such a way where it can like process millions of combination, a quantum computer can easily break through most of our current infrastructure's encryption easily. It's like go through. It's like, oh, this is your password, A, B, X, Y, Z. No, it's like it will not even try. Like it's like, yeah, it goes through. It's like encryption is not even there. So people want to make encryption that are much more quantum proof. And you might be like, when I say proof, I mean in the same way how our normal computer cannot break through a complete algorithm. It's like it will take, yes, quantum computer can break through it. It will take them like 100 years. Same. So same thing for encryption. It is very necessary. And right now Cisco and all other companies, they are working in such a way that they can enforce their encryption in such a way that yes, quantum computer can break it, but it cannot break in 10 minutes. It will break that in like 10 days or 50 days. Now that is a very big margin, because if you can figure out that even the best quantum computer breaks it in 50 days, for a damn fact that no hacker is running around with like a quantum computer in his backpack. That's not happening. So that narrows down who the heck hacked you. So that is why encryption is such an important thing. And then we come to the the money maker for every Tom, Dick and Harry else, including the people who make the money, the high variability mathematics. Now again, this is dumb way, there is a mathematical way to say that, but this is all there is to it. Is that if you have to find x, and x has x equals y plus z plus a plus b plus c, so to c square to minus probability, and all of them have probabilities. It's like finding a roadmap, exact roadmap. It's like go from point A to point B. How many traffic signals you have, how many states those traffic signals can be at, because they can be red, they can be yellow, or they can be green. So there's three states, and all these three states will pile up how much time it's going to take. So a quantum computer can handle all those variables in the one go. It's like I processed all the way, like either you're going to reach in 12 minutes 59 seconds 28 milliseconds. Like it can be that accurate. So high variability, basically you will see logistics, stock market, all that jazz, quantum computer can handle that. And protein folding, now if somebody figures this out, like we're gonna reach on a second level of human evolution. It's like protein folding is the main bottleneck right now for our medication. We know how to solve 100% of issues, like from HIV to cancer and all that jazz. We know how to solve this. It's just we do not know how to precisely deliver it. It's like we have a weapon that can take care of it. It's just we do not know how to deliver it. Chemotherapy takes care of the cancer, but it also nukes everything around you. Same happens with every other drug. We know we can, if we can get a little bit of aluminum in the right place, boom, done. So there are many easy way to solve problems, even including problems of our brain. We just do not know how to do it. Like we do not know, okay, these areas are behaving this way, how the heck I dump reduce electrical interference here, and then everything else will work. Because right now all our instruments are blunt instrument. Once we understand how the heck protein works, how the heck protein allows certain chemicals to go through or not go through, because our brain has what you call blood brain barrier, we can make medication that is, rather than brute force destroys everything, oh, you are on a medication, you're like, I'm a zombie, yeah, I'm fixed, but my brain is not working properly. Instead of that, like precise, a sniper. So amazing probabilities lie if we can unlock quantum computers. Now, I have already flown you. Let's bring you down to earth. The reality is we have nothing. Right now, we do not have quote unquote quantum computer. So you know, like what the hell is there? Like D-Wave, what is IBM Q and Microsoft, all that jazz, like what the heck? Those are what we classify as basically research tool. They are quote unquote Raspberry Pi. They are not products out of it yet. Yes, they are actual quantum computers. Yes, they work, but they do not compute in a way where you're like, okay, I'm gonna buy this and I'm gonna put this in my lab and it's gonna do research for that. Right now, every company who is buying all these things from Lockheed Martin and all that, they're buying that to understand how the heck quantum computer works. Because if you can solve this, like why you may be like, why the heck Lockheed Martin wants that? Simply because if they can, Lockheed Martin, I'm saying Northrop Grumman also have them. If they can figure out atoms structures behavior in a metal fabrication system, they can make a metal that is thin but indestructible. That would be awesome for a fighter jet. So there is a lot of behavioral properties that we have to understand on a quantum level to reliably utilize that. Quantum computer is the best tool, and you cannot expect that oh, I'm gonna buy like 10 years from now. You will be behind schedule beforehand. And what if China starts to do, which they already did, it's like they already pumped billions, not millions, billions of dollars into teaching quantum computers and making them. So they are making sure they have people ready for quantum computers when the quantum computers are ready. So they are like working on both hands. So all these companies from IBM, Microsoft, Google, all of them are working so well because this is the next waters. They are working to make sure that they can they are at the forefront of it, because whoever cracks this first, they can use one quantum computer to make another quantum computer, because you cannot use classical computer to figure out a quantum computer. It does not work that way. But you can make a classical quantum computer give you the best basically IC configuration for a, let's say, next mobile processor using quantum computer. So people are jumping into it, like they're like, let's figure this out. This is the biggest what you call human infrastructure improvement ever. So that is why right now we do not even have a hardware design, because when I say computer, I can be reasonably sure you thought of silicon, and I can be reasonably thought the design, the logic gates are the same, and every processor, be it ARM processor, be it x86 processor, be it RISC processor, all of them follow the same damn architecture. When you're talking about something here like silicon processor, there is no such thing. Some people have developed a silicon based system, some people have developed a rubidium based system, some people have developed something else, niobium, weird names. Basically, no absolute answer exists at this point. Right now, we are in a phase where we do not know which one is the best. Some are like, hey, it's cheap to make because it uses silicon. Some is like, hey, it's niobium, it's much more stable in temperature fluctuations. Because when you're talking about something that low, it's like a big plane flying above will heat up that much. So weird things are like that. So no insulation is perfect, so you have to design in a such a way that it is tolerant to that. Like some other designs are like very tedious to make, but they are much more error prone, basically error proof. They do not have random errors to strip through them. Right now, if you actually read the documentation, it's like, yeah, it's 64 notes are there, and it's like half of the notes are dedicated for error correction. So the reality of it is right now it's a research phase. It's like fusion reactor. When somebody says fusion reactor, it's not real. We do not have fusion reactor. What we have is a tool that's like we're testing it. Can we fuse material? Yes. Can we break even? No. Like right now record is like, oh, we had plasma, stable plasma for 50 minutes. Oh, 50 seconds. So you can understand right now it is in the same phase. It's exactly stuck in the same place where fusion is right now. So we do not have hardware design where we like, okay, this is how we're gonna make it. Nope, we do not have. Now algorithms. Now this is the main brain storm of that. Because of the when I said about that quantum encryption, I provided a video down below which is ludicrously complex, and your smoke may come out of your brain, but you can understand that because it exploits superpositions probability of an atom itself to break any encryption. Now again, encryption that is working on non reinforced encryption, normal encryption right now, normal encryption, and yes, it can break through because it can exploit exploit superposition. Do we have algorithms like that for everything? Do we have algorithms like that for DNA protein folding? No, we do not. That's what these people are developing, because let's say you build a tool but you do not have any way to exploit superposition, it's useless. So we do not have algorithms. Like, yeah, we have one or two algorithms, not everything, but you also have to understand quantum principles have a lag over point. Basically, before that certain threshold, using a classical computer is better. So do not expect quantum computer to replace your servers. It just not make does not make that much sense. It may be in the back end optimizing the search engines, it may be back end optimizing the neural networks, but will it be the front end? It's not suited for that. Like, it can do that, it's just not suited for that. It's like you are wasting energy. So we haven't even made algorithms for everything. Then you also understand this is normal for things. Because of the hype, because of the internet, we think like, oh, we had this yesterday in the lab, today we're gonna have it. No, it takes years. And that's why I keep coming back to the same example. It's like Einstein came up with a laser, some engineers came up with the actual laser, then some other people, actually clever people, came up with that, like, hey, we can use this, we can turbocharge our shopping industry using barcodes. Things happen, things take time, a very long time. So right this point in time, you can easily wait 20 years before anybody can say, hey, give me this quantum computer with this variant and all that, just, and you can have, like, oh, I'm gonna run an actual protein sequence equal to this. Like, you can just feed into, like, everything has to be sorted out from the computing language to programming sequence, because right now the computing language is more or less like a Python. You need proof of that. I have provided the IBM's quantum, like, it will help you understand how the heck they are making production, basically production, I'm saying, programs relying on probabilities rather than absolute statements. So that is a very good exercise. If you want to understand it, please watch that video. But the reality of it, right now, it's very far away. Those people who are going into basically universities right now, and if they are choosing quantum computer, only they will actually understand like how far away we are from actual making production. And there is a CNBC interview also, which actually shows from people from all these companies. They're like, yeah, we started, it's just like very long way to go. So this was my presentation on basically quantum computers. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends, that will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me an extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.